Hi, welcome to the Power Quality Lecture Series. Today we are going to see the voltage cycle magnitude with one cycle voltage sag. This is another method. So the another example of voltage sag corresponding to three phase is this. This is the time domain plot of one cycle plot of three phase voltage sag. So for a three phase system, when the fault is appearing one of the phases, so you call it as A, B, and C. Is phase A, phase B, and phase C. And fault is available like short circuit or whatever it is, or sudden loading, what you call, is available in phase B. So obviously, what we are seeing so far is there will be a voltage sag. But when coming to the three-phase system and fault is appearing on one of the phases, you can see here the voltage sag is available in phase B. But at the same time, a slight transients are available in remaining two other phases which are non-faulted phases. So this is one of the type of voltage sag for three phase, especially when fault is appearing on one phase. The voltage is low in one B phase for about one cycle and recovers faster after that. The observation is that the other two phases shows some tangent phenomena. Why you are calling it tangent phenomena? Because you can't exactly say whether it is a sag or swell. You can see sag in the sense a decrease in magnitude, whereas swell is in the increase in magnitude. So here you can't say exactly in the non-faulted phases whether this effect is creating a sag or swell. So these are a little bit of slight tangents. This is the another okay. So the next one is for the half cycle RMS voltage sag for the same three phase. So when you're considering half cycle voltage sag, what you can observe here is when there is a fault in phase B, again the same thing in middle phase B. During the same time, what you are able to see is you are able to see a slight swell in remaining two non-faulted phases. So these are the two different other types of things or types of voltage sag coming to a three phase. We can see this what we can is interpreted here. We can see that voltage in two non-faulted phases show a small swell. Due to the short circuit of the short duration of the sag, the almost voltage does not have a specific flat part. Already we have seen even in a single phase during the sag, the voltage is not a constant. And here also, here what we can observe in the three-phase system is also due to the short duration of the sag, the RMS voltage curve does not have a specific flat part. This makes the determination of sag magnitude data arbitrary or a little bit of difficult. It implies if the monitor takes one sample every half cycle, resulting the sag magnitude can be anywhere between 26 to 70%, depending on the moment at which the sample is taken. Okay. In case a one cycle window is used to calculate the RMS value voltage, the situation becomes worst. The two alternate methods for obtaining the sag magnitude versus time have been applied so far to your phase B of the event. So the two voltage waveforms, what you have seen, the two different methods. Okay. So this is the voltage sag per unit per cycle. This is the half cycle by using the half cycle fundamental component. The mathematical expression you have seen already in previous sessions. So now it's all about obtaining the voltage sag. So now why we are talking this is we would like to mention the voltage sag as an quantity or quantification, like what is this much of sag, because all this graphical representation is not that much of understandable for a normal person, but we would like to make it more simple the sag in terms of percentage. We'll see that. Until now, we have calculated sag magnitude as a function of time, either as RMS voltage, either as peak, or as fundamental component obtained over a certain period of certain window. There are various ways of obtaining one value for the sag from the magnitude as a function of time. Most monitors, what they do is they take generally the lowest value. When the sag needs to be quantified in a number, one common practice is to characterize the sag to the remaining voltage during the sag. So this, how we can do is this: a 70% of the sag in 230 voltage system means the voltage has dropped to 161 volts. That means you can say 70% of sag 230 into 70 divided by 10 of 0.230 into 0.7. It is 161 volts. So this is the simplest way how you recommend or how you say or how you quantify a sag. And this method of characterizing a voltage sag is recommended in the number of IEEE standards like 499, 493, 1998, similarly 1159, 1995, and 1346, 1998. Okay, there are different IEEE standards where we follow because the nation. This is one of the best method. If you say 20-80% sag in a single phase system, it gives 230 into zero point 0.8. This is how you can simply quantify your sag. So again, this sag we can quantify into two different terms. One is the deep sag and then is shallow sag. What is the deep sag is? The deep sag is a sag with low magnitude. For example, like around 10% of actual voltage or 20% of actual voltage, 10 to 20%, not exactly 10. You can let's low. Similarly, shallow sag has a magnitude of a largest magnitude around 90% of actual voltage. Okay, if the sag voltage is around 90%, you can call it as shallow sag, whereas it's only a low magnitude, and you can call 10% of actual voltage, you can call it as deep sag. Okay, so for this, what we are doing is we are taking I'm taking a distribution network with the load positions. I'm taking here 4 loads A, B, C, D. I'm taking transmission systems from which sub-transmission from this distribution and low voltage. So what I would like to do is, so I would like to explain this distribution network with different loads and fault positions. So I'm talking, in order to make you clear understanding what I'm taking is, I'm taking, I indicated here A, B, C, D. These 4 are the loads, A, B, C, D, whereas this 1, 2, 3, 4, 5, which are indicated in the circles, or the faults. Okay, so I'm considering fault at each level: transmission system and sub-transmission, distribution, low voltage, and all. Let us see when the fault is at each different positions and how does the sag appears for different types of ABCD loads. Let us start with the fault at 1. So a fault in the transmission network, that is at the position number 1, will cause serious sag for both the substations bothering the faulted line. So these two substations which are bothered here to transmission line. What will happen is the serious sag will be applied for these two substations. Okay, this sag is then transferred down to all the customers which are connected to this. As there is no generators connected at a lower voltage, there is nothing to keep up the voltage. The result is that you can see there is no voltage which are connected here. There are only voltage connected to this particular position A, and once this sag is available to all the customers which are connected here, there is no other generators which are connected to boost up the voltage sag. Okay, the result is that the deep sag is experienced by all these A, B, C, D. Okay, and this is one thing. The sag experienced by the A is likely to be somewhat less deep than compared to remaining these 3. Can you anticipate the reason why, or why I make a statement here that the sag experienced by A is little bit of less when compared to B, C, and D? Can you anticipate the reason why it is so? Yeah, exactly right. The reason why I'm saying is you can see other A, the generators are connected, and these generators will boost up a little bit of voltage sag. And hence, when you compare this sag at position A or load A with respect to ABC, the sag at A will be less when compared to remaining this one, remaining B, C, and D. Okay. So the sag is likely to be somewhat less deep as generators connected to the substation will keep up the voltage. Okay, this is the case. I think you understood. So let us what simple is because the fault in a transmission system. These there are two substations which are connected here, and this effect will be on both. And as there are still other stations connected to these other loads, the deep sag is followed or absorbed in all the loads. But whereas due to the availability of generators at the load A, the sag when compared to PC and D is somewhat more in compared to load A. Let us move to the fault during at the subtransmission level. That means at the position 2. So this will not cause much drop for the customer A. The impedance of the transformer between the transmission and subtransmission. Okay, the impedance of the transformer between the transmission and subtransmission systems are large enough to considerably limit the voltage drop at high voltage side. This is the high voltage side, isn't it? This is the high voltage and this is low voltage. So the impedance of the transformers is considerable enough to limit the sorry, to limit the voltage drop at high voltage side of the transformer. The sag experienced by this, but still the sag experienced by the customer A is further mitigated by the generators feeding into the local transmission substation because of the generators. Okay. The fault at position 2 will, however, cause a deep sag at the both the substations and this both the substations and also all the customers fed from here. That means for B, C, and D. Okay, it is clear. Now, can you anticipate when the fault is at position 3, that is around your distribution side? Yes, somewhat good. When the fault is at position 3, exactly 3, this will cause a deep sag for the customers D, followed by a short circuit or long interruptions after clearing of the fault. That means when the protective devices are clearing the fault, what will happen is once the fault is cleared, it is followed by short interruptions or long interruptions. This customer C here will only experience a deep sag. The fast reclosers is used in the distribution system. The customer C will also experience two or more sags shortly, one after the other, for a permanent fault. The customer B, here the customer B, will only experience a shallow sag due to the fault at position 3. Okay. Whereas the customer A will probably not notice any effect from this fault at position 3. Okay, is it clear? So I'd like to summarize once again. The customer deep sag is for customer D because it's very near, you can see. And because it's very near to this fault, what will happen is there might be some short or long interruptions which are repeatedly occurring after the clearing of the fault by using the protectors. Whereas here C is also connected a little bit close here, will experience an deep sag, and if fault reclosing switches are used in this, the customer C will experience two or more sags continuously one after the other. But this B here, it's only a shallow sag that is only 90% of the initial value. And whereas A, it's the chances of any effect of this fault on A is almost all very thin, and you can say very null. Similarly, now if you can see when the fault is at 4, the deep sag for this, because this is very near to this is C, a deep sag for this customer C, and for this it is connected to the customer, customer D, we can anticipate an shallow sag. Whereas again, the D and A are almost all not having an effect. Similarly, if you can take down the fault at position 5, the vice versa of for position 4, because very near customer D, a deep sag for the customer D, and its distance is somewhat near for some for the customer C will have an shallow sag. Whereas again the same thing, because the fault is here, the B and A will have almost all null effect or minimal effect, or you can say null effect for this fault at location 4 or 5. Okay, this is how the sag behaves for different loads which are being connected at the different positions for different loads in a local distribution network. Thank you.